In this video, we're going to look at another logic problem. And in this problem, we're going to introduce a new technique called considering global constraint. Sometimes the global constraint is implicit, which requires us to dig in, to think carefully. Now, the global constraint sounds fairly abstract. So let's use the following concrete problem to see what it really means. So the problem: Alex, Ben, Chloe, and Dan play a ping pong tournament. Every pair of two players played exactly one game. Every pair of two players played exactly one game. We know that Dan won against Alex, and Ben, Chloe, and Dan won the same number of games. This sounds important. Question: how many games did Alex win? So first, please allow yourself several minutes to think this problem yourself. Assume that you have spent the time. Let's see how we approach this problem. So first, let's introduce some notations or representations to help our thinking. And the notation is going to be fairly common for this kind of questions. We're going to use a node to represent a player. So node A represent Alex, node B represent Ben, and node C to represent Chloe, node D to represent Dan. And for a pair of players, when they play a game, we're going to connect the nodes. For example, A and B is going to play a game, so AB going to connect it. And BC is also going to connect, CD is going to connect, DA is going to connect, and as well as AC and DB, because every pair of two players played exactly one game. So we know that all those four nodes are connected pairwise. And we're also going introduce an arrow on this connection. By the way, this connection we're going to call an edge. So we have a node to represent the player, an edge, which the connection between the nodes is representing a game. If A wins over B, we're going to introduce an arrow pointing from A to B. So for example, we know that Dan won against Alex. We're going to point this arrow from D to A. Okay? So the direction is from D to A means that D won against Alex. Now from here, it's immediately clear that the total number of games it played among those four players is 6, because you can count it. 1, 2, 3, 4, 5, 6. So totally there are 6 games. Now just think about it. In every game, there will be one winner. So that means the total number of games won from the player's perspective, the total number of games A won plus the total number of games B won plus the number of games C won plus the number of games of D won is going to be 6, because there are totally 6 games, and in each of the games there's only one winner. So the total number of games A won plus number of games of B1 plus number of games C1 plus number of games D1 is going to be 6. And this is a global constraint. The problem did not tell you, but that you can figure out by just understanding the problem. Now we want to figure out how many games Alex won, this number. So now, if we can figure out number of games B1, number of games C1, number of games of D1, we can figure out this because of this global constraint. And the problem tells you the number of games B1 and the number of games C1, D1 are the same. So which means that these three quantities are the same, right? So now, can we figure out the number of games B1, which of course equal the number of games C1, the number of games D1. Can we figure out this? If we can figure out this, the problem is done. Okay? So now this is the key problem we're trying to figure out. And from here, this graph representation of the games, there's another constraint that it's fairly obvious. For any player, how many games does he play? Does he or she play? From Alex's point of view, he played against B, plays against C, plays against D. So for every player, there are 3 games each player played. So 3 games each player played. That means for every player, you at most have 3 wins, which means the number of games B1 is going to be less than or equal to 3. At the same time, the number of ones, of course, is bigger than or equal to 0. But the fact is Dan won against Alex. So the number of games D1 is going to be bigger than or equal to 1. Which, okay, let's using a variable to represent this common thing. The number of games B1, number of games C1, number of games D1. Let's using a number, let's call it a D, okay? Just represent the number of games D1. So D is going to be bigger than or equal to 1 because D won against Alex. So he won at least 1 game, but at the same time less than or equal to 3. Right? Because each player only played 3 games. Now, let's think about the 3 cases. Because D is going to be less than or equal to 1, bigger than or equal to 3. D is bigger than or equal to 1, less than or equal to 3. Is it D possible to be 3? If D equals 3, that means the number of games B1 is also 3, number of games C1 is also 3. So 3 plus 3 plus 3 is 9 already, and that's impossible, right? Is it possible D equals 1? If D equals 1, that means the number of games B1 is also 1, number of games C1 is also 1, and that means the number of games A1 equals, this is 1, this is 1, this is 1, so it means this number of games A1 is 3. So which means that Alex wins against everyone. But because Alex lost to Dan, the number of games A1 cannot be more than 2. So this is a contradiction. So this is also impossible, right? Is it clear? Number of games, if we assume the number of games D1 is 1, that means this is also 1, this is also 1. That means the number of games A1 is equal to 3 because they add up to be 6. But the number of games A1 cannot be 3 because if it's 3, that means it wins everyone, including Dan. But we know from the problem that Dan won against Alex. So that leaves the only possibility D equals 2, meaning that Ben won 2 games, Chloe won 2 games, and Dan won 2 games. Because now this is 2, this is 2, this is 2. That means number of games A1 equals 0. All right. Now let's see if it's actually possible in this. In here, Ben going to win 2 games. So everyone Dan win against Alex, Chloe won against Alex. And in here, B won 1 game, D won 1 game here among these 3, and C won 1 game. So if you count the number of games B won, he won 2. The D won, he won 2 against A and against C. And C won against A and against B. So in the end of the day, in this problem, Alex won nothing. He did not win any game. Actually, a bit of extension on this problem. Here, the total number of games for 4 players is 6. What if there are 100 players and every pair of 2 players play exactly 1 game? And this is a problem that has been stated in counting the segment is exactly the same problem. If we think about from the perspective of each player going to play 99 games if there are 100 players. So the total number of games will be 100 times 99 divided by 2 because every game is double count.